Okay, today we're going to talk about a system called KVin, and I want to be really clear from the get-go, this is not another research paper. This is a production engine built to solve one of the biggest, most expensive bottlenecks in AI inference right now.
45 gigabytes. That's the VRAM cost for just one user, on one GPU, running a top-tier model with a long context window. It's the hard ceiling on your throughput, and if you're running inference at scale, you are feeling this exact pain every single day. Now look, we've all seen the papers, right? TurboQuant, KVin, Gear KV, the algorithms are definitely out there. But the research code, you know what I'm talking about? Python name tuples, no real lifecycle management, and absolutely no production infrastructure to speak of. They show it's possible, sure, but they don't actually solve the operational problem. And that's where KVin comes in, and I really want you to think of him this way. KVin is less of a product and more like a new senior engineer on your team. You know, the one who just quietly comes in and takes care of the really hard infrastructure problems so nobody else has to worry about them.
So on that same 70B model, KVin saves 30.5 gigabytes of VRAM per session. Now, a number like that should immediately make you ask a question.
Right. How does a single developer build something that entire well-funded teams haven't managed to ship yet? Well, the answer isn't some revolutionary new algorithm. It's about experience. A lot of it.
You see, the core of what makes KVin work is actually way older than this whole AI boom. It's built on a foundation that's been battle-tested for decades.
The core architecture is from a high-throughput caching platform that was first built back in 2001. We are talking about 895 files of C++ designed to handle millions of events a second with sub-microsecond latency. And here's the crucial insight. The problems of that old system, append-only data, time-index lookups, real-time queries, are structurally identical to managing a KV cache on a GPU today. This wasn't a rewrite from scratch. It's a direct port of a proven architecture. And this quote from the developer, Stephen Williams, just nails it. He realized that every single pattern he'd spent years hardening for mission-critical systems mapped perfectly to what was needed for inference memory. This is just a story of incredible leverage. The right experience applied at exactly the right moment.
So, with that history established, let's look at the actual engineering here, because this isn't a prototype. This is a real production-ready system.
Just take a look at the stats. Over 8,000 lines of C++ and CUDA across 53 source files, 3 custom kernels for quantization and attention, and honestly the part that matters most to anyone running at scale, a full test suite with 89 tests, all passing. This is not a script. This is a serious piece of software engineered for reliability. Let's dig into performance. For something like position lookup, a standard hash map gives you what, 30 to 50 nanoseconds of latency? KVin uses a 3-level radix tree. That gets it down to just 1 to 2 nanoseconds. At 128,000 tokens, that gap is an eternity. And how does he manage memory? With a proper arena allocator. It's a bump pointer system. A huge block gets pre-allocated, and new allocations just bump a pointer. The benefit is massive. 0 malloc calls on the hot path, and you get an O of 1 reset between requests. No fragmentation, no garbage collection pauses. It's the same pattern that ran on 2001 hardware, and frankly, it's faster than what most ML teams are shipping today. And KVin isn't just a brute force compressor. He's intelligent. This chart shows his per-head adaptive precision on a QN model. What he's doing is measuring the entropy, the complexity basically, of each attention head in real time, and then he assigns only the bit width it actually needs. In this case, he saw that more than half the heads could get away with 2-bit, while the rest needed 4-bit. And this all happens automatically, 0 manual config.
Okay, so the engineering is solid. But what does all of this actually get you? What is the payoff at the end of the day?
3.67x. That is the overall compression multiplier. We're not saying nearly 4x. The number is precise, 3.67x. So what does that number actually mean? It translates directly into higher throughput. It means you can serve 3.67 times the number of concurrent users on the exact same hardware you already own. This isn't a theoretical gain. It is a direct increase in your capacity.
And what does that mean in terms of dollars? Let's make it real. For a pretty small cluster, just 10 H100s, that extra capacity works out to an estimated $1.2 million in annual savings. The ROI here isn't just fast, it's pretty much immediate.
So look, you could try to build this yourself. Your team is smart enough. But you know as well as I do, this is a project that would take 2, maybe 3 of your best GPU engineers about a year to get right. So the real question becomes this. What is 12 months of your GPU team's time worth? What else could they build for the business if KVin were already taking care of this for you?